Good morning, everybody. I'm Marco Bevilacqua. I'm the team leader of Armonia Group for this last period of the project. Armonia name comes from the name of the daughter of Ares, since it's a mission on Mars, and also recalls such a concept of coordination between different subsystems, because our mission is quite complex. I will briefly talk about our mission, so a brief overview, and then let the word to my colleagues who will speak about first mission analysis and then the different segments of our mission, and finally we conclude with the mass budget and power budget, risk analysis, and finally the conclusions. So, starting from the inputs that of our mission, we have to exploit aerial platforms on Mars atmosphere to perform in situ measurements to collect high-resolution data in Mars atmosphere, and also to deliver a distributed sensor on Mars surface to collect also seismological and other ground data. All this has to be done with some constraints. In particular, we have to visit peculiar regions like Valles Marineris and Hellas Planitia, and also the polar caps during the period of sublimation. All this trying to obtain an operative lifetime of at least 2 years, and some other constraints related to the launch date and the data relay. Looking more in details to the phenomena we are going to observe, we have divided them into three major regions. First, in the tropical region, we would like to observe the genesis of local dust storms, dust tables, other phenomena like the sources of methane. And in the polar region, where I would like to observe for sure polar cap sublimation, and again the source of methane. In addition, we would like to observe remotely the residual magnetic field of Mars. Our mission is based on mainly the use of 3 superpressure balloons as aerial segment. This is our choice. We decided to deliver them 2 in tropical region and 1 on the polar cap. This allows us to reach the 2 years operational lifetime, since the lifetime of single balloon is not sufficient to cover the whole mission. This is not done continuously, but at least they will cover the most relevant, scientifically relevant periods on Mars. We will also rely on dedicated entry vehicle, 1 entry vehicle for each balloon. Thus, we can inflate balloons directly in flight. This is the most, you can say, promising technique for inflating balloons. And but this will also allow us to have a sort of flexibility on the regional deployment of our balloons, and also in the time deployment of our balloons. We can deploy them directly on the regions we would like to visit without the need of guidance to reach the most peculiar regions. And we can also try to reschedule the mission if something goes wrong, for example. So it gives us robustness, flexibility, and adaptivity. We'll also will rely on an orbiter who will act as a balloon tracker, and will also collect data and send them to Earth. Finally, we will have 2 ground stations that will be released from the 2 tropical entry vehicles. They are quite massive, that's why they cannot be carried by the balloons, and that's the only, let's say, weak point with respect to the requirements we were given, because we were asked to have 4 ground stations, but that was not possible unless we let them be carried by the balloons. So having a quick look about the dimension, on the dimension of our mission, we have a ground station which is in the order of less than 1 meter, a balloon that will be more than 30 meters. They are different, the tropical and the polar. The polar will be a bit smaller. The gondola, which will be hanged behind the balloon, which will be in the order of 1.5 meters, and the overall segment composed by the orbiter and the entry vehicle attached in series will be in the order of meters. So finally, we will have also GEMS as a technological demonstration. GEMS are nanoscale sensors. They were first thought as an alternative to balloons, but then due to their limited lifetime and their and some telecommunication issues, they have been discarded and then reintroduced as a technological demonstration. They can be released by balloons in a peculiar period or during some relevant events. There are also representative models of the sensor. Having a look to the time scale of our mission, we will mainly have 3 phases. After the launch, we will have the transfer from Earth to Mars. Then we will have an aerobreak of about 150 days to save more or less propellant and make the mission feasible. And then we will have the 2 years of operational lifetime, ending with the disposal. Having a look more in detail to the operation in the operational lifetime, we will have first a 1 month setup, which will be practically 1 month during which we will observe Mars and try to set up everything and maybe reschedule something or be some kind of adaptive to the mission. Then we will have the 18 months of measurement campaign, during which there will be released the 3 balloons according to what we have decided. Finally, we will have also a buffer slot of 5 months to have further measurements, or if the balloons will survive for a moment and what expected, we can keep on collecting data, and also from the ground station we could keep on collecting data. We could also rely on the possible of releasing balloons in common periods to try to have simultaneous measurements. The balloons are scheduled according to scientifically relevant seasons. That's more or less all. I will leave the word to Amedeo Rocchi, who will talk about mission analysis.
Thank you. So, we started from the interplanetary transfer for the mission analysis, and we had as a driver, of course, the mass maximization at the Mars target orbit, and we had some constraint on the departure date, and we selected a direct transfer since it's the most used technique, and we assumed we used the Likert-Koenig model, and we assumed the chemical propulsion, so impulsive maneuvers. We produced, for example, this workshop, and we selected the best launch date that you can see here, which has a transfer time of 310 days. Here you can see the trajectory. There is nothing special to be said. For what concerns the insertion in the operational orbit, we considered first a direct transfer to the operational orbit with one-shot maneuver, and but this gave as a result a delta V of 2 km per second. But since we have a massive dry spacecraft and the delta V is quite high, no launcher is usable to launch such an high mass with the given C3 we have. So we need to reduce somehow the delta V required to insert ourselves in the operational orbit. What we selected was an aerobraking maneuver. We selected that because it's flight proven twice at Mars. It doesn't prolong too much the interplanetary transfer. It doesn't have strong requirement in the configuration of the spacecraft, but leads to large delta V savings. So we used a simplified model for the simulation, and we neglected Mars rotation, and we assumed an exponential model for the atmosphere. And we selected some parameters. So the initial orbit, similar to the MRO mission, so with the apocenter just inside the sphere of influence of Mars, and the pericenter equal to the operational orbit we selected. During the aerobraking regime, we will have a pericenter of about 100 kilometers, and this was chosen in order to minimize the duration and have acceptable thermal and structural loads. So this is the result we get. It's a delta V saving of 1.2 km per second that lead to a huge mass reduction. And the possible issues were analyzed and solved because there were almost 5 months in order to to reach the operational orbit are okay in the mission timeline. And the thermal and structural loads were analyzed and were acceptable. Here you can see basically the initial orbit, the blue one. And then every 50 orbit, here are represented in orbit, and as you can see the apocenter is decreasing up to reaching the operational orbit in green. So coming back to the launcher selection, this was the old value with a given C3 and the mass considering the delta V of 2 km per second. and you can see that no launcher is available on the market to launch our spacecraft. But with our braking maneuver, we are feasible with the Delta IV heavy configuration, and this is the only option we have. For what concerns the operational orbit choice, we had as a driver the maximization of the time in view of the aerial and ground segment. So we took data from the simulation of the balloon motion, and we had some latitude ranges. They were taken into account. And we had some constraint on at least the possibility of deploying a balloon near the pole, and altitude of the pericenter not too high in order not to have too much drag and so too much station keeping delta V. So we have also some nice to have constraints. For example, a high coverage of Mars surface and a low altitude orbit in order to have better communication with the ground segment and the aerial segment, and to have a cheaper re-entry for the entry vehicles. Here you can see, of course, we use a trade-off in order to select the orbit because there is no other way. And here you can see the altitude of pericenter, the altitude of alpha center, the inclination, and the angle of perigee. You can see it is basically almost a circular trajectory and almost polar. Here are represented the trajectory in a Mars inertial reference frame for 12 orbital periods. And you can see here it's not a repeated orbit. So we maximize for the communication windows, and these are the results we get using simple formulas and numerical simulation, assuming a minimum relation angle for the communication of 10 degrees. So we got a minimum communication window of 7.1 minutes per Martian day, and we have a 100% of coverage of Mars surface in one day, so no blind spot for the aerial and ground segments. This is just an example for one orbital period of the coverage. For what concerns the entry vehicles, we selected a procedure in order to release them, and it's the following. We acquired a release orbit slightly lower than the operational orbit. We release the entry vehicle and the related structure, as it will be explained later, and then we return to the operational orbit. For what concerns the trajectory of the entry vehicles themselves, we had as a driver, again, the delta V minimization, and we use a model for the orbital phase and the first order Allen model for the atmospheric phase. We had some constraint on the velocity at which the supersonic parachute will be released, and also considering the flight path angle in order to minimize again the delta V and to keep the entry vehicle inside the atmosphere. And this is the parameter we selected, again with the trade-off. And this is the results we get. Here you can see an example of the three phases entry. So this is the release orbit. This is the orbital arc, and this is the ballistic arc, and this finally is the atmospheric descent. Here is an example for the Valles Marineris balloon, but they're also represented on the other two spots we're going to visit. Hellas Peninsula is on the other side of the planet. The trajectory can be defined simply by the true anomaly of their insertion starting from the operational orbit, and the release orbit. Finally, I will present the delta V budget, just the contribution I didn't highlight before. So we have to consider the trajectory correction maneuvers, the correction during the aerobraking regime in order to keep the altitude of the pericenter constant, the station keeping contribution, and the decommissioning also phase was considered. The delta V budget was also made for not only for the orbit, but also for each of the entry vehicles. I will now leave the stage to Claudio Pulsi that will tell you all about the balloon design.
Thank you. I will try to explain the process that has brought us to the design of the balloons that supports the aerial platforms. And so first of all, an analysis phase during which we have studied the environment of Mars. We have selected the technology for the balloons, and we asked ourselves if we wanted to rely on a guidance, navigation and control system on the platforms, and plus the strategy for the buoyancy of the balloon. Then a sizing phase during which we have decided computed the dimension of the balloons. We have chosen the material for the envelope, and we have at last produced two numerical models as a validation of our design, a thermodynamic model and a flight dynamic model. So first of all, for the environment, we have used as a tool the Mars Climate Database from ESA that receives as inputs space and time coordinates on the surface of Mars and gives as outputs the main properties of the atmosphere, such as density, pressures, and etc. So, for example, for what concerns the thermal environment, we have analyzed the scattering phenomena due to the presence of the atmosphere. And here you can see we have analyzed in the 4 different seasons on Mars. You can see the equinoxes scenario here, and the northern and summer and southern summer on Mars, and correspondingly the launch windows of the balloon. For what concerns the technology that we have used, we have investigated through the existing technologies, but at the end we have selected the superpressure balloon. Because the superpressure balloon is actually a balloon that has a constant volume supported by the higher pressure inside the balloon with always greater than the environmental pressure, and flies at a constant density level. The positive aspects of this technology are that it has already been used in Vega mission in 1995 on Venus. It has a longer lifetime with respect to the other technologies, and it has a simpler design because of the constant volume. And but let's say the negative aspects are related to the fact that since it has a constant volume, the buoyancy capabilities relies on the external density of the atmosphere. So gradient of density could cause a rapid change in altitude of the balloon, and the gas needed for inflation has to be brought from Earth to Mars. Helium in our case. For what concerns the guidance, navigation, and control system, actually this technology is already been investigated by NASA, and as a sort of a wing attached very far below from the balloons, in order to experience a different condition in the atmospheric properties, and to produce force that could direct the motion of the balloons. Of course, with this technology, we could have optimized the exploration capabilities of the balloons, and also perform maybe maneuvers to avoid impacts from the orographic obstacles. But we will have also increased the complexity of our system, increase the mass, and also increase the dimension of the balloon, since the long tether needs, of course, a higher floating altitude. So we decided not to rely on GNC system, but rather on free motion of the balloon. So a proper design of the floating density of the balloon was needed. So, as I said, the superpressure balloon flies at a constant density level. So we have to choose the criteria, the density through some criteria, and we have created a model of isodensity surface in the atmosphere of Mars, and marked them with 2 performance indexes, such as the altitude experienced from the balloon. There has to be as much as low as possible in order to perform good quality measurements, but not too low in order to avoid the impact on the obstacle. So that are the 2 performance indexes. So, for example, for the tropical balloon, we have made a compromise on the percentage of the orographic obstacles at at the density of this value, and an altitude that is low enough to properly do the scientific operations. And so, as you can see, we have also visible criteria to observe the result that we have got. So, for what concerns the balloon sizing, we have followed the static dimensioning through the Archimedes principle and exploited the two concepts on which the superpressure balloons technology is based, superheat and superpressure. The superheat is the delta temperature across the envelope of the balloon that must be inside the assumed values, and the superpressure, of course, is the delta pressure across the envelope that must be always greater than zero. And so with that, those as inputs, we have come out with the actual sizing of the dimension of the balloon. For what concerns instead the material, we choose to rely on a composite envelope material in order to match all the requirements such as strength, stiffness, in particularly permeability of helium, because we wanted to increase the lifetime of the balloon. The UV resistance, that is a major concern on the atmosphere of Mars. And so we have selected 3-layer composite material, low density polyethylene on the external side, in the middle of a fiber spectra, and inside the mylar. Two design, one for the polar balloon and one for the two tropical balloons. And actually, the tropical balloons, as I said before, are bigger because they rely on a lower floating density. In order to validate the assumption on the superheat and super pressure, we have made a thermodynamic model of the balloon, considering all the thermal sources, including the internal reflection and transmission and convection natural inside of the balloon and forced outside, considering the winds. And we had to check the superheat delta temperature actually was always under an upper limit, and a super pressure higher than a lower limit. And we checked that design actually could work. As a last tool for the validation, we have made a fluid dynamic model of the motion of the balloon, extracting from the mass climate database a mesh for the atmosphere of Mars that receives that for many points on the surface inside in the atmosphere and in time gives out as the information on the characteristics of the atmosphere. And we have simulated the vertical motion and the horizontal motion in order to understand if the correct altitude was reached, and also if actually the guided navigation and control issue was discarded for a good reason. We have also extracted from the simulation interesting results for the EPS subsystem, such as the sun elevation and simultaneous exposition of the balloons, for the thermal environment, for the thermal control system, and as I said, as Amadeo said before, the ground track formation analysis. And these are two examples of the motion of the balloon. Here you can see the starting point in the red dots, and this is the first launch from Hellas Planitie. And this is the second launch on the North Pole. You can see the balloon descending caused by the sublimation of the CO2 from the polar caps that creates the currents towards the air. And this actually helped us on discarding the GNC hypothesis, since we have seen that the balloons actually perform the required let's say motion. So now I leave the word to Vincenzo Pesce that will talk about the payload of the balloon.
Good morning. We talk about the gondola, that is the core of the AMO segment. So you can see that we have to perform some analysis and to observe some phenomena such as the polar cap sublimation, thus the industrial formation. And for this reason, we have selected this kind of instruments that always have a high TRL, except for the ultrasonic wind sensor, the micromima, that is a spectrometer that was developed here at PoliMI. Then going to detail, we have the gondola attached to the balloon with a 500 meter tether, as you can see also it works. And this is mainly for the reason for avoiding the shadow of the balloon on the gondola itself, and because of communication, in order to allow communication between the gondola and the orbiter. Going to detail of the configuration, the main driver of the configuration is the power requirements, because we have to face the low irradiance levels present on Mars. So we have to have larger solar rays area in order to also to satisfy the constraint of the volume, the limited volume of the entry vehicle. We have decided to have a truncated pyramid with extendable body-mounted arrays. And so, going to detail of the configuration, we have this kind of electronic box with a radiator in the bottom part connected with its switches. Here we have the instrument, so the spectrometer, the UNICAP, and the ultrasonic read sensor is attached to a deployable boom in order to not have any noise from the structure. Then we have the antenna, and then from this view we can see the gems, the jettisonable gems, and the camera. The video where we can see the deployment of the solar rays and the deployment of the boom here, the boom of the wind sensor. Going to detail of the subsystem, we start with the electrical power subsystem because it's the main driver for the configuration. So we have decided to have a classical, reliable photovoltaic system with 4 extendable body-mounted panel. And the secondary battery, we have decided to use a lithium-ion battery. We have also decided to have a sizing strategy for this kind of subsystem because fixing the area and knowing the radiance during the day, we know also the available power for our system. So knowing the value required by each subsystem in each mode, we can try to fit the shape. Here we have science mode and telecom mode that are the most requirement that requires more power of each mode. So we can always satisfy the requirements in terms of power with our available power. So here we have the power budget and the mass budget of the system. We have decided to use a PCDU as a PCDU, a direct energy transfer with a regulated bus, mainly because of the presence of the lithium-ion battery. Then we have the thermal control system that is driven by the low power available. So we want mainly to remove heat from the hot equipment during daylight, but we want also to minimize heat losses during night. In order to do this, we have decided to have a night thermal insulation, also a variable thermal conductive path. Going to detail of the configuration, we have this box, the electronic box, connected to the radiator, as already said, with 4 paraffinic switches. This is allowed to dissipate during daylight the heat from the electronic box, but also to decouple the electronic box from the external environment during night. We have also the electrical meters unit here and also on the wind sensor in order to heat up the system, and also 5 TH. With this kind of configuration, we can see how we can respect all the temperature range for each element, both in the worst code case and the worst code case. Here we have a mass budget and a power budget. We have decided to don't use MLI because of dust and atmospheric issues, and we are focused on the study of the thermal conductive path because it's critical for a strong design of thermal control system. Then we have data. We have collected data and we have to manage data, so an OBDH system is needed. So this is the architecture of the OBDH. We have a primary bus, data bus, and a redundant one connected to the attitude and to the payload. Then we have a remote terminal unit in order to manage the data that we have. We have two processors working not redundancies. These are 6000 base 32-bit. Then we have the storage, so memory 16 gigabyte. Here, the article of the telecom. So we made a study on the Martian atmosphere. So focusing on the losses and the attenuation, mainly related to the fog clouds, aerosol, and dust storms. In this graph, you can see how in polar and valleys region, the losses are almost equal depending on frequency. But in southern hemisphere, during the storm, the losses increases a lot. We've also made an analysis on an equivalent noise temperature, considering an upward-looking antenna and downward-looking antenna. With an upward-looking antenna, we can see how the equivalent noise temperature is lower, so we have decided to use this kind of configuration. Going to detail of the link budget, we are constrained on the power, the amount of data, and the visibility windows depending on the orbital motion. So we have decided to have this signal over noise ratio, considering margin and considering also the wanted bit error rate. So considering losses and the equivalent noise temperature, we select this frequency mainly because of the losses and the low power available. So this is the results for concern the linear transmitter, so two linear antenna, because to have a true coverage between the orbiter and the gondola, we use the receiver a parabolic antenna of 3 millimeter. So this is the results of the data rate from the link budget. You can see how this red line is the data that we have to transmit. This is the data that we actually can transmit, depending on the distance between the orbiter and the gondola. So we see how in the first place we cannot transmit enough data, but then with the peaks we can manage also this situation. So we compensate initial phase. We can also see how in that storm we cannot transmit almost anything. So this is not a good solution. It's not a good situation for our telecom subsystem. So in tropical balloon and polar balloon, we can transmit enough data. During the storms, we can't. Then we made the Fintan model analysis in order to evaluate the loads, the response to the loss of the structure. So simulating our structure, we evaluated the load, so gas loads, heavy braking loads, and also the wind of the extended panels during the storms. We have seen how no yielding, no buckling, no deflection of the boom tip occurs during the storm. So I will leave the stage to the last part and will explain you the ground station of our mission.
Good morning, everyone. I'll be talking about the ground station, also known as the Moses. Starting with the configuration, we had two main drivers for the configuration that we selected. The first one was the ground station had to be small enough to fit inside the limited volume of the entry vehicle. And the second one being the solar panels which were used to power the instrument should have been big enough to last the entire lifetime. Based on that, what we decided on was the cylindrical disc configuration, which was 25 centimeters high and 87 centimeters in the diameter. It was divided into two sections. First, the top half contained the 4 deployable solar panels, which would be deployed whenever needed. The second half was again divided into two sections. One called the bomb box. As you can see, it contains all your batteries, PCDU, amplifier, and the electronic equipments, while the second half contained all your instruments and the sensors needed for the mission. As you can see in the demonstration, once the ground station touches the surface, first off, the solar panels are deployed. Secondly, we have a robotic arm which will be used to deploy the seismometer on the ground to avoid any sort of noise in the data. Then we have also considered using telescopic booms to deploy all the environment sensors so that there is no interference from the ground station to the readings. As you can see, we have a linear antenna also, and this displays your pressure sensor and the temperature sensor booms. Moving on to the electrical power subsystem, as you already saw, we had 4 deployable solar panels, which were accompanied by a secondary battery. This was mainly driven by 2 factors. First was the specific power, second was the reliability of the system. And the idea was here to meet the power demands during each mode and phase. This was computed using the peak power consumption, and as you can see from the graphs, the highest power needed was during the telecom phase, followed by the science phase. So what we did was to try and restrict all our high power activities at the time of availability of highest power, which was between 10 and 3 in the Martian hours. And the blue line here clearly states that the available power at that moment was way higher than what was needed, and we were able to satisfy all the requirements. Then to conclude with the EPS, I show you the mass and the power budget. And to add up, we used a PCDU with a direct energy transfer with a regulated bus. Then talking about the thermal control, here the main idea was same as that of the aerial segment, to keep the components in their temperature ranges by minimizing the heat loss while also radiating any extra additional heat that was generated. However, one important drawback, or let's say limitation for the ground station, was its contact with the Mars surface. And during the night, that would have acted as a source of sink and depleted the ground station of all the heat. To overcome that and all the other problems, what the strategy was applied was use of aerogel all over the surface for insulation, then adding up a radiator to the circumferential area of the warm box, which was controlled by 2 paraffin-based thermal switches. Then to heat up the system, we had 1 electrical heating unit and 5 radioisotopic heating unit. And to finally cover it all up, we wrapped it up in golden coating. Then multi-node analysis was done on that configuration, taking the worst case for both Halus Malaysia and Valles Marineris. And as you can see from the graph, the purple line indicates the operating range, and we were clearly able to meet all the requirements. Then to conclude the thermal control subsystem, I show you much in the power budget. And in this case, I'd like to add one of the proposed technology here was to use mini loop heat pipes to guarantee a uniform distribution of temperature, and it being as a lightweight alternative. Moving on to the onboard data handling. In this case, the main driving factor was the selection of the sensor suites that we had. And since we had mass limitations, we tried to find the sensors which had built-in application-specific integrated circuits. As a result, what we decided on to use a single electronics board that would contain a processor capable of delivering 25 megahertz. It was connected to the sensors using a 1553 data bus, and all the data was managed using an integrated remote terminal unit. Finally, we had a local data bus to connect the RTU with the processing units, and a 16 GB of onboard storage to store all the scientific data. Finally, to transmit all the data, we move on to the telecom subsystem. In this case, since we had no regulation on the bandwidth usage on the Mars environment, the main drivers came from the power available to the system, which was around 7 watts, and the losses which were specific to the Martian environment, as mentioned earlier. So taking that into consideration, we took a signal to noise ratio of 8.6 dB, and we came up with a frequency of 400 megahertz, which was transmitted using a 0.7 meter long linear antenna and received by a 3 meter wide parabolic antenna on the orbiter. As you can see from the graph, the top one represents your link budget, while the bottom one represents the amount of data transmitted. The green line in both cases represents the amount of data that we were able to transmit during the dust storm, which was not feasible to do. However, under normal circumstances, as you can see, the orbiter gets closer to the ground station. We had a peak in the data transmission over here, and we were clearly able to transmit all the data that was generated during the mission. Then to continue from here, I invite Marco Ciarambino.
Good morning, everyone. I will guide you throughout the most critical part of the whole mission, probably. That is the entry vehicle entry, the descent of it, the partial deployments, and the balloon itself that is deployed and demonstrated. So we can divide this macro phase in 3 sub-phases. So the first one, the entry vehicle atmospheric entry. The second one, the deployment of the parachute, the supersonic parachute. And the third one, the subsonic probe inflation with the parachute, with the balloon inside. So this is a sketch for the whole phase. 1, 2, of course, are the entry vehicle. 3, 4, the supersonic parachute deployments. 5 and 6. The subsonic probe release, the violet one, very big, as you'll see, with inside the balloon inflation. So starting with the first one, we consider the entry in the atmosphere of the entry vehicle at an altitude on Mars of 110 kilometers. And one major constraint was to assure a velocity at 20 kilometers in altitude below 400 meters per second, in order to assure correct deployment for the supersonic parachute. And actually, we have managed it quite well, because from the simulations, in 281 seconds of exploitment of the drag of the entry vehicle, we arrive at 368 meters per second. We experience a maximum acceleration during this phase of 3.1 Earth Gs, so 9.881, and that's it for the entry vehicle. Then, at the end of this phase, it's released the supersonic parachute, that is a 6.5 meter in diameter disc gap bend type. It's pretty big, but it has to do its job. In 40 seconds of operation, we arrive from the 20 kilometers altitude when it has been deployed to 13 kilometers in altitude, lowering the velocity down to 110 meters per second. Then we enter the most critical subphase of all, that is the inflation of a very huge subsonic drop, as I say, the violet one. Here the system is composed actually by, we can see three main subsystems: the balloon here in red, actually here is inflated, the subsonic drop, the violet, and a pre-parachute that is a cross-type parachute. In the drogue, in the envelope, you can see these are scoops in which ram air can be taken in order to have a proper displacement working with the pre-parachute. And there are two main jobs that has to fill the subsonic drogue. One, of course, to slow down our system. As you can see, being it's really huge, it can slow down to 22 meters per second. And second one, to prepare a protective environment for the inflation of the gas cell. So this phase lasts for 120 seconds when inflation must occur, so very strict time. And there is a maximum acceleration experience of 9 Gs actually when it's deployed the subsonic probe. Anymore. Okay, sorry for that. So we can see that inflation is completed, if you have seen before, at 9.5 about kilometers in altitude. At this point, we need to release the subsonic drogue in order to provide the steady state flight for the balloon. So what we have in mind, we first of all release the ropes here. They are nylon-made ropes with USA military standards, nylon-made. There is the rip-off of the stitches here, as you can see, and with the help of the ram air intaking from below and through the pre-parachute that is still deployed, we have the slip-off of the whole drogue. That is because we complete the inflation before reaching the steady state density of 8,000 meters. This is the case for the tropical balloon. Actually, the polar one is even lower, so it's even better. The stitches rip off, the drogue slip away, and we have the complete steady state flight for the balloon. We need 15.5 kilos of helium that must be inflated in 120 seconds. So here is the mass flow rate, 130 about grams per second. And so where is Moses? Where is our ground station in everything here? Moses is attached to the back of the heat shield. So towards the end of the supersonic parachute phase, it is released, the heat shield, with a touch on the back Moses. Then Moses deploys its parachute. After deploying its parachute, that is a disc gap bend type model as the one for the supersonic one for the entry vehicle. There is the detachment on the entry vehicle and relative structures that are still attached, I remember, at Moses. And then before touching the ground of Moses, airbags are inflated in order to have a correct impact. These are main parameters for the parachute. As I said, it's a disc gap bend type. And these are velocity profile for the descent, acceleration profile with a peak of 3.5, less than 3.5 Gs, Earth Gs also here. And this is the altitude. It's quite linear because steady state on the descent, as seen here in acceleration, is reached quite fast. And the overall descent lasts for 515 seconds when of course the impact. This is the brother of the rendering behind me. Beautiful Moses. And now let's talk a bit about the entry vehicle, the inside of the entry vehicle with its subsystems. We have 12 helium tanks dedicated for the inflation of the balloons. These are radially and equally spaced displaced in the entry vehicle, as you can see. There is the propulsion subsystem pressurizing and feeding system here. So 2 tanks for the non-methyl hydrazine and 2 tanks for the nitrogen tetroxide, with 2 tanks of helium for the pressurizing system. There is Moses, our ground station. So as you can imagine, this is one of the tropical balloons because it has Moses inside. There is the gondola in its folded configuration with folded solar panels here and here. We have the 2 parachutes. The red one is the supersonic one, and the yellow is the subsonic one. And we have the balloon cell, as you can see, quite big. So what we have done to validate our shell of the entry vehicle, we performed a CFD analysis to validate also our models for the descent, and we used through a computational fluid dynamic analysis using CO2 flow. Actually, Mars atmosphere is 97% in CO2. We obtained a drag coefficient of 1.45 that in literature is quite accurate because they're usually between 1.4 and 1.5. We have a neat flux of up to 5 watts per centimeter square. You can see the Mach number and the maximum temperature reached for the fluids. That is, of course, as you can see here in front of the heat shield. Well, this is just sketch. It's quite hard to see, but the Mach number here is up to 781. Velocity contours with the shock flow, and here is the flow temperature as already states. So what we have done instead with respect to the structural analysis through a finite element model, we designed an aluminum alloy shell, taking into account the gravitational acceleration and the pressure that has to be sustained during the descent. Due to the very thin atmosphere on Mars, we have a pressure during the descent, a peak pressure in the dynamic pressure of 3,500 pascals onto the heat shield, with an acceleration inside for the various masses of 17 Gs. So numbers were really small, but I say stresses here are very, very far from the aluminum yield stress value. We are about 9 megapascals of stress maximum stress onto our structure. And in order to have an even more conservative design, we just modeled to sustain all the loads the external shell without considering any internal reinforcements. So with internal reinforcements, even better the situation. Talking about instead about the attitude control system, we have as a requirement for the precision landing to have a no lift component or the aerodynamic force, and we provide this with a PID and pulse width pulse frequency modulation controlling our force secondary thrusters. And we have as a main goal a pointing error with respect to velocity error of the vertical axis of our entry vehicle, less than 1 degree. And we obtain a very, very nice value that is actually lower than 0.3. Here, disturbances has been modeled with a strong white noise, and so the system stiffness is proven. Here is a sketch for the torques for the moment about every principal axis of inertia of our entry vehicle. And then we talk about the propulsion subsystem that has to be performed. The orbiting kick and the attitude control, as already said. As you can see, H delta V has been tailorized by Amedeo mission analyst for every entry vehicle in order to save mass, because our main driver is always mass saving because of the huge components we have on our mission. So as you can see, there are 3, 1, 2, and 3 in red main engines radially disposed that are provided by Aerojet. They are in class of 110 Newton, paired with a secondary subsystem of 1 to 3 and 4 in purple here in the sketch, from ETS Astrum, that's our 10 Newton class to attitude control. The overall system is a bipropellant system, of course you saw, monopropellant and nitrogen tetroxide. And here on your right hand side you can see a sketch for the direction of the flow of the secondary thrusters. So it's 48 degrees here, you can see inclined with respect to the vertical axis to provide torque, and here the spinning capabilities if needed. So this is the sketch for the pressure regulated system. It uses mainly latch valves to control single seat latch valves to control the secondary propulsion system, and double seat latch valves instead for the primary propulsion system. This is the mass budget here on top. As you can see, they're quite similar, but we have actually saved about 15 kilos more or less, tailoring every one of the entry vehicles. For what concerns electrical power needs, we have a peak of less than 300 watts that occurs during the detachment, and so with the primary and the secondary secondary systems acting of the propulsion system. So latch valves, double solenoid, and so on. And now I leave the word to Andrea that will talk about demos.
Thank you. When we dealt with the configuration of our orbiter, the main concern that we had is the position of the three entry vehicles that are quite massive, and therefore they will be deployed in a long time. And so we try to maintain the spacecraft as balanced as possible, because we made some simulation and the altitude control system would be too big in order to control the unbalanced configuration with another disposition of the entry vehicle. So we decided to align the entry vehicles with one axis of the spacecraft, that will be the nadir pointing axis, in order to enhance the gravity gradient stabilization of the altitude. We fixed the panels orthogonal to the nadir axis in order to allow the rotation around the nadir axis to maintain the solar panel as close as orthogonal as possible to the sun, without two hinges with two joint with two axis control. The nadir Mars antenna, that its orientation is controlled by the altitude control system, and to fit inside the launcher we need the foldable solar array and the retractable antennas. Moreover, for what concerns the structures, that was another main problem for the orbiter, we cannot attach anything to the heat shield of the entry vehicles. All this configuration has a major drawback of complicating the mission if one entry vehicle's deployment will fail. As I say, this is our orbiter with the three entry vehicles aligned, the two solar panels. This is the nadir pointing antenna that is fixed, just deployed, and then the altitude control system pointed to Mars, and the measures of the whole spacecraft. This is the one main section. You can see the main body of the orbiter is devoted to maintain and have the propellant tanks and pressurized tanks mainly, and all the minor instrumentation, and the external reticular structure to feed the three entry vehicles. When we deploy the first entry vehicles, obviously we will deploy also the reticular structure that protect the second entry vehicle. In order to perform this maneuver safely, the main hinges keep the orbiter on a safer orbit, far from the reticular structure that has been released. And this mitigate the risk of the mission, because if, for example, the entry deployment system of the first entry vehicle fail, we are anyway able to detach all the structure and release always and anyway the second entry vehicle. For what concerns the internal instrumentation, we have mainly as I say, the Mars antenna that is just deployed, the Earth antenna that is two-axis control in order to point the Earth without affecting attitude requirements. We have the radiators and the star sensor that are aligned obviously along the solar panel axis in order to minimize the pointing to the sun of these components. One of the 6 pair of reaction control thruster, this one is the one that makes torque around the nadir axis, and all the internal instrumentation, transmitter, OBDH, PCDU are or inside the thin substrate of aluminum that is not well seen in the picture, that is folded with MLI and so protect thermally the instrumentation, or if they can be lower this part, they will be folded with MLI. This is the operation around Mars with the Mars pointing antenna, the two-axis control left antenna, and those are the only instrumentation that carry the orbiter. The orbiter is mainly a deployer of entry vehicles, but we fit this phase to install 2 cameras and 1 spectrometer to perform anyway analysis on Mars. This is a representation of the deployment of the antenna. Actually, this is turn 180 degrees when it hit the launcher with the feed toward the entry vehicle and not starting in this video. But this is the final configuration that we obtain when everything is deployed. The attitude dynamics control system drive mainly the configuration of this orbiter as I just said. We have a nadir pointing mission basically, and the Earth antenna do not impose any requirements on the attitude dynamics control system. We only require the nadir pointing mission with nadir pointing error less than 1 degree and a rotation around the nadir axis to maintain the solar panel orthogonal to sun within 5 degrees. We need maneuverability for the deployment because we have to reorient all the main engines to perform the safe maneuver. We need to be stiff during the air braking, the fire modes, mainly during the air braking with the huge big panel that we have. We cannot vary our attitude. And we envisage an emergency maneuver if one entry vehicle will fail its deployment. We can be able to have an emergency slew rate of 1 degree per second with all the 4 reaction wheels that we have and the 12 reaction control thrusters. Indeed, these are the architecture of the attitude dynamics control system with 2 star sensors that provide the main attitude determination, 8 sun sensors that provide almost full coverage of the environment, and they will be used in safe mode and to acquire the initial attitude. The big 4 reaction wheel that provide the maximum torque of 0.4 Newton per meter, and the 6 pairs of reaction control thruster. We try to maintain, however, the dry mass as low as possible, also the nominal power as low as possible, and we have only a peak power that is quite high for the emergency maneuver just presented. These are one simulation when the orbiter acquired the attitude starting from an initial wrong condition. It is able to acquire the attitude well below the imposed limit because we have 0.1 degree of error in nadir pointing, less than 1 degree of error in sun pointing, and this maneuver is made in 750 seconds. The reaction wheels have to perform this work in order to perform the previous maneuver. The second main concern about the orbiter is the structural part, because we have to provide an external support for the 3 entry vehicles without attaching anything to the heat shield. The design case is the inertial loads that are present during the launch, obviously, but with these huge masses attached to a so thin structure, we have a lot of problem to meet frequency requirement of the launcher. But we perform the analysis, we satisfy and we perform the static and bucking dimensioning, and then the modal analysis to avoid resonance with the launcher vibrations. So those are the constraints, the attachment to the back shell, minimum frequency, and we conclude with aluminum strut structure with aluminum panels reinforced anyway with bulk. Those are the inputs, so the flight envelope of the launcher, the delta for EV. We made a finite element method analysis to perform this computation, and we also checked that the aerobraking loads are withstand by the solar panels with these solar panel substrate, and this is not a problem mainly for the hinge because we obtain this flexural momentum at the root of the solar panels. This is the result. These are the result of the simulation. The maximum displacement is well below the requirements from the launcher, so below 5 millimeters. The maximum stress is also acceptable, and mainly we are able to provide higher frequency with respect to those required by the delta 4 EV. According to the mission analysis, we have the delta V to be provided by our main propulsion system, and is mainly after the launcher injection in Mars transfer orbit. It is only in charge of our main propulsion unit with 1.2 thousand of meters per second of delta V provided. Obviously the main engines are posed very close to the center of mass to avoid attitude disturbance in case of failure. The 6 pair of secondary thruster to perform all the control maneuvers, and the class of 890 newtons MMH NTO primary propulsion system, and MMH NTO 22 Newton thruster for the secondary propulsion system. This is the sketch of the propulsion system with the two main engines. It's pressure regulated and basically contains all the stuff that we need to make work the system. With the mass budget that is obviously the most relevant for the whole mission, because 1.7 ton of mass for this system, obviously for the propellant, and peak power consumption of 140 watts to make all the valves and pressure regulation system working. For what concerns the thermal control system, we have a narrow temperature range to satisfy, and mainly we have to face different configuration after the entry vehicles are deployed. For this reason, we implement the thermal control system that has to be stiff to external variation for the different phases of the mission, obviously, and all is regulated on the global insulation to localized dissipation. And this is the solution with the entry vehicles that are actually covered by MLI to protect them during the transfer. We have the radiators that are installed with louvers to control and better control and tune the deep space dissipation. And however, we need 365 watts of electrical heater units to maintain mainly the payload of the entry vehicles warm enough. Those are the situations that we have to face. The disappointing attitude during the interplanetary transfer makes our most full case, because we have only this phase exposed to sun and all the rest of the spacecraft exposed to this phase. And then on Mars we have normal configuration for what concerns the thermal income. So as I say, the cold case is during transfer for some pointing altitude. while the hot case is when Mars is at perihelion and our orbit is without eclipses because of the right ascension anomaly. But anyway, we are within the ranges of the instrument because obviously this is the transfer with the coldest body temperature, and the panels have the highest body temperature because they are continuously pointed to the sun. While around Mars we have the situation with 3, 2, 1, and 0 entry vehicles. Obviously, the first entry vehicle we are always well below the required limits. In this situation, the entry vehicles protect somehow the body of the orbiter from dissipation. We lose one entry vehicle. Then when we lose another entry vehicle and another entry vehicle, we have the body that is still colder because of the more area exposed to the deep space. And so the body needs more power from the heaters. This is the design and the thermal control system. We need quite amount of MLI to protect all the body and all the entry vehicles with the louvers, and the power needed by the heaters, mainly for the reason that I explained before when all the entry vehicles are deployed. We make a very robust thermal control design because we take into account the possible degradation of the MLI during the aerobraking maneuver. So we consider the MLI with very low performances because we consider the possible degradation of these materials during the aerobraking. And as I said, also the entry vehicle needs MLI insulation to protect their payload. Now Silvia will present the last system of the orbiter.
So starting from the OBDH, that is the core of the software part and data handling of our system, the requirements of this subsystem are the high on autonomy, the survivability to high radiation doses of the components, and the high payload data rate that it has to manage. And these high level requirements has to be satisfied considering constraints given by the TRL of the available components, the limitation that we have on the overall mass of the system and of the power, and the compatibility of buses that we want with high speed with the components we selected. And the solution is found considering using latest available units and components that should be radiation tolerant. Another requirement, as you can see here, is the tracking and positioning of AMOS, that is the aerial platforms. And this was solved using algorithms for tracking these objects. Looking to the architecture of the OBDH, it is done with a distributed bus to grant high reconfigurability and redundancy. As we can see here, it is made with 2 data management units to control as a control. The first one dedicated to attitude control and housekeeping data, and the second one dedicated to payload data. And each one is made by 2 processors in order to have redundancy. Inside the DMU2, we have the tracking algorithm implemented, while then we have an RTU connected to the DMU2 in order to have connection between the sensors and the platform. And then we have the 2 memories to store all the data. And here are some components that have been selected and the tracking software we selected to use. All the data collected on the orbiter comes not only from orbiter itself, but also from the other segments, since the orbiter acts as a relay between the segments and Earth. So with the constraint of this quite huge amount of data to be transmitted, and the constraints on the power supplied to the telecom system, and in order to grant the signal to noise ratio desired, we perform a link budget, selecting as the downlink frequency the 32 GHz, and with a 3-meter diameter parabolic antenna and as a deep space network as a receiver. What we get is that this is the total amount of data we can transmit in blue, and in red the total amount of data that we should have to transmit, obtained taking into account again the constraints that comes from mission analysis, that is the number of visibility windows and the duration of each one. But as we can see, we are able to transmit all the data we have within the visibility windows we have. And at the end, I want to present you the EPS, since all the subsystem we have seen until now requires power. And as a drivers for this, we use the specific power and the reliability. See, the specific power in order to not increase the mass too much, and the reliability in order to not increase the risks, since the mission is quite risky by itself. And the design relies on 2 solar arrays and a secondary battery. Since the requirement of the propulsion system, the power subsystem, is to support the power demand for both average and peak loads for each mode and each phase, we performed a power budget, and as we can see here, the most demanding phase is the telecom one, and this is not only the most demanding one, but also a recurrent phase, since it can take place once per orbit. And so the sizing strategy was to consider the power in daylight the one required for telecom mode. This is the budget we did with a solar array area of 23 meters square, and the selection of the batteries that are secondary batteries lithium ion. And since they are very sensitive to charge and discharge, we selected as a PCDU with a regulated bus. And at the end, we did an additional analysis in COMSOL model to simulate the arrow braking, since the drag increases the heating of surfaces. And the condition we selected is with the rear face of the panels oriented in the direction of motion during the arrow braking. And as we can see here, this is a simulation. Here is the area where cells are placed, and this is the substrate. And as we can see, the temperature is lower at where cells are placed, and it never goes, and it's always under 150 degrees. For this reason, we decided to put all the wirings and connectors on the front face of the solar panel, and that each material and process for the array must be investigated for its ability to survive at these temperatures for multiple exposures. Now, there is a massive power budget, since both has been for the overall project. Some drivers we have to take into account, since this is for AMOS, one for the tropical and for the polar balloon both. And as you can see, they have quite a huge mass. And while moving to the entry vehicle, the mass increases a lot, and that's why it has been a driver for the overall mission. And then here is the overall mass budget for demos with both the dry and wet orbit, for wet and dry mass. And here a total considering the margin and the adapter. And looking at the power budget, we have done for each subsystem again, considering also a dust storm mode for both the MOSIS and DAMOS, as you can see here, in which we have just to survive, since we are not able to do anything else. And here is the overall budget for DAMOS. And now, to draw some conclusions, as we can see here, these are the most critical aspects of the project we have talked about until now. And as we can see, the most critical aspect is the inflation of the in-flight inflation of the balloons, since it has a low TRL, and this means that we have to reduce this risk index, and this should be done with the test campaign in a similar environment to the one we could find on Mars. And the other are other risks we can have in our mission, but with a lower index. And considering all these critical points, not only about the low TRL of the inflation technology, but also to the lifetime of aerial platforms and to the low number of ground stations, since we have a requirement of 4, but we are able just to have 2. We can say, by the way, that mission is feasible because all required scientific data are collected. So that's the end of our presentation. Thank you for your attention. And if you have some questions.
Just one short question because of So I suggest you have a very short question now for them, and then at the end of the whole presentation, if still something wants to be asked to the team, can be done. Otherwise, we go on.
We can ask that if they have some beautiful video of the beautiful t-shirt.
For you.
I
mean, maybe it's
how did you find the last component?
Sorry, there is one technical question, otherwise we jump to the other. For the air braking phase, which driver would you consider design phase?
We try to maximize the area of the spacecraft, but taking into account that to lower the risk, we thought of the attitude being with the entry vehicles aligned with the velocity vector. So, like this, if the velocity vector is in this direction, and this is the attitude for the aero braking, with the panels reversed, and the driver was trying to have the loads in order not to have a too strange configuration and to minimize the time somehow.
From the point of view of the loads to be there, we consider heat flux.
Yeah, we consider the heat flux on the back of the panels and the load on the panels because they are
dynamic pressure.
Yeah, the dynamic pressure on the panels and so the torque that is on the engine itself. They were very fast.
Okay, thanks again to the team. I invite the Galaxy Ranger to come. So the Galaxy Ranger wants to come or want not to give the presentation?